Hello, welcome back. Today, we're going to take a look at Chapter 7, which involves conics. Now, there's a couple sections here, but they're all very similar, so we're going to go through them all at once here. And the idea is that what we're looking at is what is called conic sections. If we were to picture ourselves with a double-ended cone, and we were going to cut slices into the cone, there's a couple of different shapes we could get. If we slice this way, for example, we could get a circle. If we slice at slightly of an angle, then what we end up creating is an ellipse. We could also consider slicing this way and create ourselves a parabola. And we could consider slicing this way, where the slice goes across both parts of the cone, and we get a hyperbola. So there are four different shapes that we can make that we're going to call the conic sections. There's actually three more that we can make. We could imagine creating a single point. That's a bad color to see. We could imagine creating a single line, or we could imagine creating two lines at once if we slice like this. But our main focus is going to be on these original four: the ellipse, circle, parabola, and hyperbola. Any conic can be created with the generic equation ax squared plus bx plus cy squared plus dy is equal to k. But what we want to do is we want to make these equations a little bit more specific so that we can get more information from the equation in its simplified form, graph it, and determine what type it is just from looking. Let's go through all the examples, and we're going to begin with the simplest one, a circle. A circle has a center of h comma k and a radius r, which of course needs to be positive. So let's say that this was our point, hk. The circle would be all of the points. That's a terrible drawing. That's better. A circle would be all of the points at a fixed distance of r. So every point on this circle would have a distance of r away from this center. And we would say that this would be, say, the point x comma y would be the point on the circle. Now, we could very easily come up with an equation for circle by just using the distance formula. Here, what we have is that the distance from hk to xy is equal to r. So distance is equal to r. That means that the square root of x minus h squared plus y minus k squared would be equal to r. This is by the distance formula. By squaring both sides of the formula, we obtain x minus h squared plus y minus k squared is equal to r squared. And this is going to be the standard equation for a circle, as printed here in a little bit more detail. We can use this idea to create the equation of a circle given information, or vice versa, to graph an equation if we know it's a circle. Let's go through a couple examples. We'll start with this one, x plus 3 squared plus y minus 5 squared is equal to 16. The only real work we have to do here is notice that 16 is equal to 4 squared. So our radius will be 4, and our center hk will be negative 3, 5. Remember that since the original equation has minus and minus, that a positive indicates a shift to the left, and a negative or a positive indicates left or down, whereas a positive indicates up or right, just as it did when we were talking about transformations. As a result, what we will obtain is x, y. We have gone left 3 and up 5 with a radius of 4. So what I like to do is I like to go down 4, left 4, right 4, and then up 4, and that will allow us to create the circle. When you're drawing a circle, the things I want to see is the center labeled, and make sure you label enough of these points that it's clear you know what the radius is. I would say the top, bottom, left, and right are good ones. You do not have to fill in the names of these points, but just make sure that you've got a dot mark so that I know that you know what the radius is. Let's go through another example. This time, for this equation, it's not in the correct form, so we'll have to transform it. And what we're going to do is we're going to complete the square. May have been a while since we've completed the square, so we'll include a couple of completing the square examples in this lesson. The first thing you're going to do is you're going to move any constants to the other side and group the x's and y's together. So we will here say 3x squared minus 6x plus 3y squared plus 4y is equal to 4. Next, we're going to factor out the greatest common factor of each piece, but only the numbers. We're going to not touch the variables. So this will give us 3x squared minus 6x plus 3y squared plus 4y is equal to 4. Next, we will complete the square by adding the missing piece. Recall from the earlier section that the missing piece we'll need to add is going to be b over 2 squared. So that'll be 6 over 2 is 3 squared is 9. And over here, 4 over 2 is 2 squared is 4. So we're going to need to add 9 and 4, but each of these is in parentheses, so there's 3 9s here and 3 4s here. So I'll add 3 times 9 and 3 times 4. On the left-hand side, we can factor each piece. It is a perfect square, so it will be 3x minus 3 squared plus 3y plus 2 squared. And on the right-hand side, 27 plus 12, 39 plus 4 is 43. Is that correct? Let's just double check. 27, 31, and 12, 43. That looks good. Finally, what we'll go ahead and we'll do is we'll divide by 3. So the final equation is going to be x minus 3 squared plus y plus 2 squared is equal to 43 over 3. That means that our center is 3 minus 2, and the radius is square root of 43 over 3. Now, we'll want to estimate this value or approximate it in a calculator because we're not going to be plotting these points exactly, of course. So 43 over 3 comes out to be a little bit larger than 14. The square root of 14 comes out to be a little bit less than 4. We end up getting 3.8. So we'll go ahead and we'll create our sketch, 3 and 2. So this seems like a reasonable scale. X, Y, we'll do 3, 2 like here. And then 3.8, so this is 3, oh, excuse me, negative 2. I need to go down. And then we'll go 3.8, so we'll go 1, 2, 3, almost 4, but not quite. Same deal, up and down. And so this ends up being our circle. Should have left myself a little bit more space, but that's okay. Now that we've got circled covers, we're going to expand our ideas a little bit and allows us to consider a slightly different shape, which is going to be called an ellipse. An ellipse says, given 2 points and a fixed distance, the ellipse is the set of the points where the sum of those distances is fixed. So unlike in a circle where we only have one distance to keep track of, Here we have 2. So we have got a point 1 and a point 2. And what the ellipse is going to end up being is all of the points where the distance here is some fixed value. So if I call this D1 and D2, let's say D1 plus D2 adds up to D. This would work in any place. So I could go here and here, where this is D1 and this is D2. We could go here and here, or here and here. And the idea is that the total sum of the distances should always be the same. These points are called the foci, and that fixed distance is just called the fixed distance. There's no special word for it that we're going to concern ourselves with. The equation for the ellipse you can derive by using this relationship. We're not going to pay much attention to it. There's only one thing that we are going to note, which is that the foci are going to end up being symmetric in the ellipse about the center. There's still going to be a center, h comma k. And if you consider this distance, calling it A for the moment, then we've got this distance, D1, and this distance, D2. Well, notice that since this distance here is A, if I call this distance C, then this, D1, is A minus C, and D2 is A plus C, since the foci are symmetric about. As a result, D, which is D1 plus D2, ends up being A minus C plus A plus C, or 2A. We can keep that in mind as we discuss the equation of the ellipse. What we end up getting is something that looks a little bit like a circle, but with a couple of changes. This should be a K. First of all, instead of being equal to r squared, we set it equal to 1. And there's now denominators. This represents the fact that x and y have distinct radii. So we will allow the fraction to tell us what the radius is in each of these cases. The major axis is the one that's going to be the longer one, and that's the one where the foci are going to lie along it. If A is greater than B, so in other words, the larger number is below x, then the major axis is horizontal and the foci lie horizontally. And the distance will be the square root of a squared minus b squared. If instead b is the larger number, then everything is reversed. The foci is vertically placed. The foci have major axis length 2b, and the focus is given by b squared minus a squared, square rooted. Let's go through a couple examples here. For this first example, we're going to once again need to complete the square. Again, what we're going to do first is group our stuff together. So x squared minus 2x plus 4y squared plus 24y is negative 33. Then we'll add the stuff to both sides. For this one, it's simply 1. For this one, we've pulled out a 4, which leaves us with y squared plus 6y plus the blank, therefore, needs to be 9, which means we're adding a 1 and a 4 times 9. This ends up giving us x minus 1 squared, y plus 3 squared, and this is 36 minus 33 is 3, plus 1 is 4. This 4 should still be here, so when we divide to equal 1, what we obtain is x minus 1 squared over 2 squared, because divided by 4, plus y minus 3 squared over 1 squared. Now, you don't actually have to write the over 1 squared, but it's very helpful because it'll tell us a lot about this ellipse. Here's what I see. Center is going to be 1 comma negative 3. I dropped this negative here, but it's y plus 3. The major axis which is horizontal, has a length of 4, excuse me. It'll be 2 going out either way from the center. And the minor axis, which is vertical, has a length of 2. We can therefore find the focal length, C, which would be the square root of a squared minus b squared. So this would be 2 squared minus 1 squared is the square root of 3, which comes out to be, I think it's around 1.7, but let's double check to be sure. If I take the square root of 3, yes, it's about 1.7. As a result, here's what our sketch will look like. We're going to need a center at 1, -3. The vertical distance is 1, the horizontal distance is 2, so this ellipse is not very large. We're going to have an ellipse that goes out like so. So the center is 1, -3. Then we've got this distance of 2 and this distance of 1. We can also label the focus with this distance of square root 3. There is a focus on both sides, so we'll put 1 on both sides. This is the kind of detail I want to see for an ellipse. The center marked and labeled, the major and minor axis labeled, and the foci labeled with the distances on the foci put in. With all this in mind, we can also go backwards. Let's this time consider where it gives us some information about the ellipse. Foci at plus or minus 5 and vertices at plus or minus 8, both with 0 as their x-coordinate. So first we'll just draw on what we know so far. I think a label of 2 maybe makes sense here. So 2, 4, 6, -2, -4, -6. So our ellipse is going to go like so. So this will be the center. H comma k has to be 0, 0. We know this because the center always lies both directly between the vertices and also directly between the foci. Speaking of which, our foci are here. Now we can use this information to find the other direction's distance. We know it's going to be horizontal for the minor axis. What we're going to do is we're going to say that c squared is equal to, in this case, b squared minus a squared, because we know that since the foci are vertically spread, that means that the ellipse has to have its major axis be vertical. As a result, we can plug in the pieces. 5 is equal to the square root of 8 squared minus a squared. 25 is 64 minus a squared. A squared is 64 minus 25, which comes out to be 44, 39. So a is the square root of 39. Should be a little bit more than 6. I got 6.2. So we can plug that in this way. 2, 4, let's make these black. 2, 4, 6. -2, -4, -6. So we'll have here and here will be our other ones. This allows us to draw in the ellipse like so. We'll create the equation, therefore. So this ends up being x squared plus y squared equals 1. We don't need any minuses because the center is simply the origin. Vertically, our distance was 8 squared. Horizontally, our distance was the square root of 39 squared. So we can just put 39 here. we'd like to, we could just put 64 here as well. It doesn't end up making a big difference. Let's go to the next one. Eccentricity is a way of determining how stretched out an ellipse is. You divide the distance from the center to the focus by the distance from the center to a major vertex. Now, if the focus is at the center exactly, then both foci are the center, the distance is fixed, and we've got ourselves a circle. So 0 would indicate a circle. The larger E is, the more stretched out it is. The foci are very far away and is a very thin, skinny ellipse. So for example, we can give a couple of sketches. Something like this would be E equals 0. Maybe something like this would be E is equal to 0.9. And somewhere in the middle, maybe something like this, E is equal to 0.4. Here, F1 and F2 are the same. Here, they're spread out a little more, and here, they're spread out even further. Further apart the foci are, the more stretchy the ellipse ends up looking, and the larger the eccentricity. Eccentricity will never be equal to 1, but it could get very, very close. It is okay for eccentricity to be 0. That simply means we have a circle. With that in mind, let's step away from ellipses for a moment and talk about parabolas. A parabola involves a point and a line. So let's give ourselves that point and that line. Here's a point. Here's a line. The parabola is the set of all points where the distance from the line is equal to the distance from the point. So that will give us this right here would be a point where that works, because this distance and this distance are the same. Let's do it like this. This distance and this distance match up. We could also have this point and this point, because this distance, oh, this needs to be further up for this to work. This point and this point, because this distance matches this distance, and this distance matches this distance. We could also have, say, a point over here, because this distance matches this distance. And when we sculpt in all the missing pieces, we get ourselves a parabola. We've got a vertex, a directrix, which is the name of the line, a focus, which is the name of the dot, and we've got ourselves what's called a lattice rectum. Which goes parallel to the directrix through the focus, and it stops at the 2 points where it hits the parabola. Now, this is very important because it gives us some information about how the parabola is going to go, how long it's going to be. Now, there's some information we can get here. The equation of the vertical parabola with a vertex h comma k and focal length of absolute value of p is given by x minus h squared is equal to 4p times y minus k. So p determines the focal length, which is basically going to determine how tall or wide our parabola is going to be. This is for a vertical parabola. For a horizontal parabola, we would essentially switch x and y. Just think about y equals x squared being our generic parabola. Since the x is squared, it ends up being vertical. We'll go through some examples here. We would like to graph x minus 3 squared is equal to 16 times y plus 1. So here's what we can glean from this information. It is going to be vertical, and it's going to be upwards facing because 16 is greater than 0. If this was a negative number in front of y, it would end up being a downwards facing parabola. Next, we are going to go ahead and we are going to determine where the center is, or not the center, excuse me, the vertex in this case. The vertex is h comma k would be 3, -1. This part stays the same for the entire section. Next, we will be looking at this p. 16 is equal to 4p. So that means p is equal to 4. This should really be 4 times the absolute value of p. No, sorry, that doesn't work because the focal length is term of p. So this is p, and that means p equals 4. So that means that the focal length is equal to the absolute value of p. This is where the absolute value comes in, is equal to 4. So here's what we're going to draw. First, we'll need to start at the vertex. We will go 3 and 1. So this is going to be x and y. And we'll start with this vertex, 3, comma. I've once again forgotten to go down instead of up, 3, -1. Next, we will look, since the focal length is 4, we can go up 4 and down 4. We go up and down because it's vertical. If it was horizontal, we'd go left and right. So go up 4 and down 4. Up 4, we'll find ourselves the focus. And down 4, we'll find ourselves the directrix. This is y equals -5 is the directrix. The focus is the point 3, comma 3. The reason the focus is up and the directrix is down is because the focus always sits inside the parabola. And since it's upwards, the focus needs to be above. Now, to give us an extra point to graph, what we're going to do is we're going to note this. This distance is 4, and this distance is 4, which means that the distance up equal to the focus would have to be 8. Therefore, we can go left and right by 8 to find 2 extra points on the parabola. So we'll need to go left here, 1, 2, 3, 4, 5, giving us this point, and then right 8 here, 1, 2, 3, 4, 5, 6, 7, 8, giving us this point here. We'll just go ahead and connect the dots from there. You'll notice that the lattice rectum has a length of 8 plus 8, which is 16. This is the biggest place where this shows up. The number, that p, is equal to the length of the lattice rectum. Half of that length is the distance from the focus to the directrix, which means half of that length is the distance from the focus to the parabola. Or I should say, from the focus to the vertex of the parabola. That's why we have the 4p show up, because the lattice rectum is the key. We'll go through another example of going backwards here. Oh, sorry, we'll do one more forward example before we do this, just to give us another chance to complete the square. And also, this time we see that since the y is squared, it's going to be a sideways parabola. Completing the square here won't take long because there's nothing for us to do with x. In that case, we're actually going to move the x to the other side. So 2y squared plus 2y will give us 8 minus x. Really, we're going to go ahead and put negative x plus 8. Or excuse me, x minus 8. The reason we want to pull this out is because we want it to look most like the form. And in the form, it's just x minus, not negative x. So we'll go ahead and we'll complete the square. Let's actually, before we do this, let's leave this out on this side. So negative x plus 8 for the moment, and we'll complete the square first. 2y squared plus 2y plus 1, negative x plus 8 plus 1 here. This will give us 2 y plus 1 squared is equal to negative x plus 9. That means that y plus 1 squared is equal to negative 1/2 x minus 9. So we pulled out the negative from here and then divided by 2. As a result, our h comma k is equal to 9, negative 1. Our 4p is equal to negative 1/2, which means that the absolute value of p is equal to 1 over 8. It's going to have a much shorter focal length than the previous one. So 9, negative 1. So x, y, go 1, 2, 3, 4, 5, 6, 7, 8, 9, and negative 1. It's not going to give us very much wiggle room here. This is the vertex. The focus is right above it. And the directrix, oh, excuse me, not above it. I need to be careful here. Because notice this time y is squared. So it is a horizontal. And notice that this time there's a negative out front of this 1/2. That means it's actually leftwards facing. So the focus is 1/8 to the left here, with a very small distance of 1/8. And the directrix is similarly 1/8 to the right. This means that the latus rectum has a length of only 1/2. So the latus rectum only goes this far, giving us a much skinnier parabola than we had last time. We can label these 2 points if we would like. So this would be, it went left 1/8 and up and down 1/2. So this would end up being 8 point, so 1/8 is 125, so 875. And then we would have negative 1 plus or minus to indicate the 2 points, 1/2. These are the 2 points that we have here and here. And the actual vertex is the 9 minus 1. As for the directrix, that would be the line y is equal to 9 and 1/8, or 0.125, except that it is x equals because it is a vertical line. Now let's go through an example where we find the equation given some information. It tells us we've got a downwards parabola with lattice rectum of -2, -7, and 4, -7. 3, 4, 5, 6, 7, 1, 2, 3, 4, and -2 gives us here and here. It's downward facing, so we know it's going to go something like this. We'll fill in the rest of the gaps in a moment. The first thing we'll notice is that this lattice rectum has a distance from -2 to 4, which is 6. This is our 4p. So p is going to be equal to, really this is 4 times the absolute value of p. P is going to equal its absolute value, 6 over 4, or 1.5. Since it's downwards, that means that p is actually negative 1.5. That's going to end up being this distance here. We'll have a distance of 1.5, absolute value of p. So this will be the starting point here, our vertex. So this is going to be the vertex, and it's going to be the point, let's say 1. And then it is up a little bit from this -7 by a distance of 1.5, so negative 5.5. The directrix, therefore, would be down by 1.5. This would end up being a y equals negative 8.5. But it didn't ask us to graph, it asked us to find the equation. The vertex is the most important piece, which we've got here. So since it's downwards, that means that x is squared. So x minus 1 squared is equal to the 4p, which was the 6, negative since it's downwards, times y plus 5.5, plus since it's negative in the y direction. There we go. only one more piece to go through. This is the hyperbola. A hyperbola is kind of like a reverse ellipse. The idea is that this time, instead of the distances from the foci being added, they are subtracted. So our hyperbola will look a little something like this. The two foci sit inside these two things that look like back-to-back parabolas, but they actually work a little bit differently because we've got a distance here and a distance here. And the absolute value of the difference is equal to this fixed value, d. We still got the concept of vertices. But in this case, we're going to get some additional pieces. The first thing we're going to get is a transverse axis. We're also going to get this piece in the middle, which we'll call the center. We also will get something which is called a conjugate axis. And we'll see how the conjugate axis arises in just a moment. For now, let's take a look at the equation. The standard equation looks a lot like that of an ellipse, but there's one very important thing. There's subtraction. This subtraction is the reason that we need to treat this differently. If it's addition like this, it would be an ellipse. If it's subtraction, it would be a hyperbola. It's also worth noting that only ellipses and hyperbolas have both variables squared. If it was a parabola, it would have just one variable squared. Let's take a look. I want to suppose that I didn't know anything about hyperbola and I wanted to plug in some points. Let's take this one as an example here. And let's suppose that there's 2 points I'm going to plug in. Y equals k, and then x equals h. If I plug in y equals k, then I will get k minus k squared over b squared minus x minus h squared over a squared is equal to 1. And over here, I'll get something similar. Y minus k squared over b squared minus h squared over a squared equals 1. In both cases, the extra piece drops out. On the right-hand piece, that gives me y minus k squared over b squared is equal to 1. I'll multiply both sides by b squared. I'll get y minus k squared is equal to b squared. I'll square root both sides, and that gives me y minus k is equal to plus or minus b. Plus or minus since we took a square root, which means that y is equal to k plus or minus b. So if this was my center, h comma k, then what I just did is I said I'm going to go up and down by a distance of b. That's the transverse axis. We'll get something similar for the other point. But here's what ends up happening. This is the piece that cancels out over here. And what we get is negative x minus h squared over a squared equals 1. This gives us, let's move the negative over, x minus h squared is equal to negative a squared. When we square root both sides here, what we get is x minus h is equal to plus or minus a, but since it was negative, there's no real solution. However, we did work with imaginary numbers, so let's make this an ai. That means x will be h plus or minus a times I. Now, this is an issue because you can't actually have this. We can't have an imaginary number on this graph. There's no imaginary axis. We only got real numbers here. So what we're going to do is we're going to mark this with an x, counting out the distance of a. Then we're going to create a box like so. where the x's and the dots are the centers of the four sides of this rectangle. Create the diagonals of this box to create what's called the guide rectangle. This will determine the shape of your hyperbola. Starting at the dots, simply use those lines as asymptotes. Therefore, the value of A is informational in terms of how wide the hyperbola will be. There's one more piece of information, the focal length. In this case, it will be A squared plus B squared, because the focus always sits inside the hyperbola, so it must be a little bit larger than either axis length. Let's go through a couple examples here, and then we'll call it a day. First, we want to graph this equation. We'll go through the math here. So here's the pieces that we need. H comma k is equal to 2, negative 3. Our a squared is, or excuse me, our a will be 3, and our b will be 5. It's going to be horizontal since it is the x minus the y. You do not care whether it is bigger or smaller for hyperbolas. You care which one is being subtracted. This, of course, should be equal to 1 in order for us to work with it at all. We can also find the focal length c. Square root 3 squared plus 5 squared is square root 25, and 9 is 34, which is a little less than 6. The square root of 34 ends up being 5.8. So the first thing we'll do is we'll go ahead and graph the center at 2, negative 3. Next, we will count in the horizontal and vertical directions in order to create our guide box. Horizontally, we're going by 3, and we're putting dots because that is going to be the real axis or the transverse axis. In the vertical direction, we're putting x's at a distance of 5. Because if I was to solve for y, I would get an imaginary number. Using these ideas, we'll create ourselves the guide box. Use this guide box to create the diagonals. And use these diagonals to loosely inform the shape of our hyperbola. Looks like it's a pretty wide one. This is because the conjugate axis is much longer than our transverse axis, which forces the hyperbolas to be quite wide. Finally, since the focal axis is about 5.8, we can put the foci at the distance of root 34 in each direction. This point right here, the h comma k, ends up being the 2 comma negative 3. We'll do one more example here, and then we'll call it a day. We want to find the equation of hyperbola with a given center, vertex, and focal length. Let's first sketch what it gives us. Center at 3, 7. Vertex at 3, 3. When it says vertex, that means one of those real dots. So we can also complete the other pieces here. This one went down at a distance of 4, so this one needs to go up at a distance of 4. It also told us that the focal length is 5, so c equals 5, which means that 5 is equal to 4 squared plus, since this is vertical, the piece we're missing is horizontal, which is a squared. This means that a will be equal to 3. Because a 3, 4, 5 triangle is effectively what we've created. 3 squared plus 4 squared makes 9 plus 16, which is 25, which is what we're looking for. So we can fill in these, which will, of course, be x's. at distance of 3 on each side, and use this to loosely give us the hyperbola. This one's less wide than the other one, more of a standard length, because the 4 and the 3 are closer together than the numbers we had last time. In any case, we'll want to go ahead and create the equation. Because it's vertical, we're going to do y first and then subtract x. We'll do y minus 7 and x minus 3 squared squared, all equal to 1. And for our denominators, vertically, our distance was 4. Horizontally, our distance was 3. Okay, that's all we've got in this section. We'll see you guys next time.